Last time we looked at Rumour spreading on the complete graph. This time we will start looking at Rumour spread on arbitrary graphs. The price we pay for this generality is that we won't be able to get exact expressions for the Rumour spreading time, but will only be able to get upper bounds. So let me start by introducing the model again for this setting. So we have an arbitrary directed graph G with vertex set V and edge set E. We denote by N the total number of vertices, and the model for Rumour spread is very similar to before. So earlier we started by introducing the model on vertices, by putting the clocks on the vertices, and then said that induces an equivalent model where the clocks are on the edges. And that approach is taken in the notes for this chapter. But here I'm going to skip that step and go directly to a model where the clocks are on the edges of the graph. Okay. As before, we start with a single node knowing the Rumour. And also, as before, there are independent Poisson processes or Poisson clocks on each edge of the graph. The process will be denoted by N. It's indexed by the directed edges VW. And it's a Poisson process with intensity or rate lambda VW. Okay. And capital lambda will denote an n by n matrix whose elements are the intensities on each of the edges of this graph. So it's indexed by an ordered pair of vertices. Okay. So G is a graph, which means it need not be complete. So many of the edges may be absent. And if an edge is absent, then you cannot have communications on that edge, so the corresponding lambda will be 0. So the graph is encoded in the matrix by having zeros where edges are absent. Okay, and as before, these are all independent Poisson processes. And they encode when the communications happen. So node V communicates with node W whenever there's an increment or a jump in the Poisson process N sub VW, when the count on that process increases by 1. So NVW is counting the number of communications between V and W, if you like. And every time it increases by 1, there's one more communication from V to W. If V knows the Rumour this time, W learns it. If V knows nothing, the communication is wasted. If W already knows the Rumour, again, the communication is wasted. Okay, so that's the model. Take a moment to make sure you understand it. The question we are interested in is again the same. What's the first time that all the nodes know the Rumour? Okay, so we are going to derive an upper bound on this time, the Rumour spreading time, until all nodes know the Rumour. And this will be stated in terms of a property of the matrix lambda. So the model is parameterized by this matrix, and therefore the time for the Rumour to spread should also depend on the matrix. And the upper bound will be in terms of a property of the matrix called its conductance. So we begin by defining the conductance of lambda. We'll denote this by capital phi, which is a function of the matrix capital lambda. And it's defined as a minimum over all subsets of the vertex set of a certain ratio. So let's look what's in this ratio. In the denominator, you have the size of S, the number of vertices in S, times the size of its complement. So that's n minus the cardinality of S. And then this product is normalized by the total number of vertices. So it's a measure of how equal or unequal the split is of S and S complement. The numerator sums up for every vertex V in S and W in S complement. It looks at the rate at which lambda, the rate at which V communicates with W, and it adds them all up. So the numerator is the total rate at which vertices in S talk to vertices in S complement. It's the total communication rate from S to S complement. And the denominator is some measure of the sizes of these two sets. And the conductance is obtained by minimizing this ratio over every possible subset of the vertex set. And we exclude only the empty set and the case where the complement is empty. In those two cases, the denominator has a 0, so this ratio is undefined. And so that's excluded from the minimum. Okay, so that's the conductance. Okay. Now our main result, which we state right away, and we'll spend the rest of the lecture proving, is the following. So the Rumour spreading time, the mean of the Rumour spreading time, is bounded by this quantity. It's bounded by 2 log n divided by the conductance. And this bound doesn't depend on which node initially knows the Rumour. You can start the Rumour anywhere, and this is the upper bound on the time for it to spread to everyone. If you compare this result with that for the complete graph, you see it looks very similar. There we had just 2 log n, and the only difference is that it's divided by the conductance. So a first question might be, what is the conductance when lambda is the matrix corresponding to the model we studied last time for the complete graph? If the conductance turns out to be 1 for that model, then this bound is exact. If it turns out to be smaller than 1, then this bound is loose. If it turns out to be bigger than 1, then this bound is wrong because it contradicts what we got last time. Okay. So before we move on to proving this theorem, we are going to work through a few examples to get a feel for what the conductance of a matrix looks like. And this quantity is defined for any non-negative matrix, meaning a matrix with non-negative entries. So let's start with the complete graph. That's going to be our first example, and let's reconsider our model from last time. If you remember, there we put a unit rate Poisson process at every vertex, and then the vertex picked an edge uniformly at random on which to communicate whenever it was activated. So that meant the rates along each edge was 1 over n. So that's what we have here. The contact rate along each edge is 1 over n. And so our matrix lambda of contact rates has identical elements, all 1 over n, including on the diagonal, because we said nodes can communicate with themselves. That's the matrix. So now let's try to compute its conductance. And remember that the conductance involved a minimization over all possible subsets. There are n nodes in the vertex set, so there are 2 to the n possible subsets. 2 of those are excluded, the empty set and the whole, all of V. So there are 2 to the n minus 2 subsets, and in principle, we should consider every one of these when taking the minimum. And as this example will show, and the subsequent examples will show, we can simplify the minimization by exploiting symmetries in the problem and trying to group together how we consider the subsets. So in this case, we are first going to group together all subsets with the same number of vertices. Okay, so we consider a subset S with k vertices and try to calculate the ratio. Now, by the symmetry in the problem, any subset of k vertices looks just like any other subset. And if you add up the contact rates along all edges where V is in the subset S and W is in its complement, then you are adding 1 over n. How many times are you adding it? You are adding it once for every ordered pair V in S, W in S complement. There are k elements in S, n minus k in S complement, so the number of ordered pairs is k times n minus k, and lambda is 1 over n, so when you add it up, you get this ratio. Okay, so that's the numerator of our expression. The denominator of our expression was 1 over n times size of S times size of S complement. The size of S is k, the size of S complement is n minus k, so the denominator is exactly the same. So then the formula for the conductance says take the minimum over all non-trivial subsets S of the vertex set of the ratio. The value of the ratio is 1. So we are minimizing the constant function 1, and the minimum value is therefore 1. So that's the conductance. The conductance is 1, and the theorem tells us that the mean Rumour spreading time is bounded by 2 log n, and this is indeed the exact value, so it's consistent. Okay. Okay, so the theorem turns out to be tight on the complete graph. Let's look at another example. The next example we are going to look at is what's called the cycle graph. So this is n nodes arranged on a ring, and every node is connected to its 2 neighbors on the ring. So one on the left, one on the right. Okay, and then we need to specify the Rumour spreading model. We need to say what the rates are for all the communications. And this is how we are going to specify it. So we are going to say that each node communicates at rate 1, choosing each neighbor with equal probability. So probability half to the left, half to the right at every attempt. So there's a Poisson process of rate 1 at the vertex. There's a Bernoulli split of that process, rate 1, probability half to the right, half to the left. And so we get 2 independent Poisson processes on the edges, and each of those Poisson processes has rate half. Okay. So that tells us that the rate lambda VW is a half for every edge, every VW in the edge set, every ordered pair in the edge set. Okay, so, so that's the model, and take a moment to make sure you understand that. Okay, so now that's the model. So let's compute the conductance for this set of rates. So again, let's pick an arbitrary subset of the vertex set with k nodes in it. And then let's calculate the sum of the rates from S to S complement. So we want to look at the total rate at which vertices in S top to vertices in S complement. Now, this very much depends on the subset S. It's not the same for all subsets with k elements. It depends where the k elements are. So if you look at, say, 3-element subsets, if the 3 nodes are right next to each other, it's different than if the 3 nodes are well separated from each other. But what are we interested in? We want to minimize the ratio, so we want to minimize this sum. for what kinds of sets S is this going to be small? Of k-element sets S, is this going to be small? It's clear that it's going to be small if the k elements are bunched up right next to each other. Because if they are next to each other, the only edges between S and S complement are at the two ends of this string of vertices, right? So there's one edge from the left end, one from the right end. There's rate half of communicating along this, rate half here, you add them up, the total rate is 1. If the vertices are more spread out, then there are more than two edges. And so the sum of half over all the edges ends up being bigger than 1. So the smallest value it could possibly have is equal to 1. And you get equality if the k nodes are all next to each other. Okay, so, so that's the numerator in the expression for the conductance. What about the denominator? The denominator is 1 over n times the size of S times the size of S complement, which is just 1 over n times k times n minus k. So the conductance now is the minimum over all subsets. And let's group the minimum over all subsets by varying k and then minimizing over k element subsets. So if you fix a value of k and minimize over k element subsets, the numerator gives you 1, the denominator gives you this, so the ratio becomes n over k times n minus k, right? So this is the minimum value of the ratio for a k element subset. And then to minimize over all possible subsets, this becomes a minimization over the integers k between 1 and n minus 1. So we are minimizing this ratio. The numerator doesn't depend on k, so minimizing the ratio is the same as maximizing the denominator. So how do you make k times n minus k big? It's easy to see that the way to do that is to make k and n minus k roughly equal in size. And depending on whether n is odd or even, you get slightly different answers. But basically, k is close to n over 2, as close to n over 2 as you can make it, depending on whether n is odd or even. And so the denominator is close to n squared over 4. So the ratio becomes roughly 4 over n. Okay, so that's the minimum value. So the conductance for large n is approximately 4 over n. And then the theorem tells us that the mean Rumour spreading time is bounded by 2 log n divided by this quantity. And then if you rearrange that, you get n log n over 2. So that's the upper bound guaranteed by the theorem. In your homework problems, you will calculate this Rumour spreading time exactly. And when you do that, you'll find the mean Rumour spreading time is n minus 1, which is approximately n. So for the cycle graph, the theorem is indeed correct. It's an upper bound, but it's off by roughly a factor of log n or half log n. Okay. So it overestimates the Rumour spreading time by roughly a factor of log n. Let's do one more example. And this is going to be the star graph. So the star on n vertices consists of a single hub node and n minus 1 leaves, each of which is connected just to the hub. Okay, there are no edges between the leaves. All the leaves are connected to the hub and to nothing else. That's the graph. And then we have to specify a Rumour spreading model on it. So we have to say what the rate of communication is on each edge. Now, I should warn you that I've drawn the edges as undirected, but you should really think of each undirected edge as 2 directed edges, 1 in each direction. And the model does not have to have symmetric rates in the 2 directions. So You are allowed to have different rates if you so wish. And I think that's what we are going to do. Okay, so we consider the star graph. Okay, so again, we are now starting by describing things from a node-centric perspective. So each node is going to initiate communications at rate 1, meaning there's a Poisson clock at each vertex. It rings at rate 1. And when it rings, you choose a neighbor at random and communicate. So if V is a leaf and W is the hub, then the clock at V rings at rate 1. There's only one neighbor, which is the hub W. We can't communicate with anyone else, so it communicates at rate 1 with the hub. What about the hub? When the clock rings, it has n-1 choices of whom to communicate with. It picks one at random. So the rate at which it communicates with any specific leaf W is 1 over n-1. Okay, so these are the rates. So again, for this set of rates, we want to compute the conductance. And we now, again, we have to minimize overall subsets. We are going to break it up by considering subsets of size k. But now we also have an additional feature. Not all subsets of size k are the same. They are different depending on whether they contain the hub and k-1 leaves, or whether they just contain k leaves. So we have to consider those possibilities separately. Okay. Okay. So we are going to okay. So we are going to consider a vertex, a subset S of the vertices with k nodes. Okay, ignore the and S bit here. Let's count the total rate at which vertices in S speak to vertices in S complement, and this is going to be different depending on whether S contains the hub or not. Suppose first that S contains the hub. That means it contains k-1 leaves, and n-k leaves are left outside. Okay, so the only communications from S to S complement happen from the hub to one of these n-k leaves. So there are n-k possibilities here, and the denominator should be n-1 rather than n. There's a typo here because lambda is 1 over n-1. Okay, so we have to add 1 over n-1 n-k times. So that's what happens if S contains the hub. If S does not contain the hub, that means S contains k leaves, each of whom talk to the hub at rate 1. So the total rate at which S talks to S complement is k. And the only vertex in S complement they talk to is the hub. Okay. So that's the numerator of our expression. And then the denominator, as before, is just 1 over n times k times n-k. And if you take the ratio and do some calculations, you see that the conductance reduces to minimizing overall k between 1 and n-1. We have to take the minimum of this divided by 1 over n k times n-k, which gives us k, and this thing divided by 1 over n k and minus k, which gives us something else. I think there are some calculation errors here. This should be n over n minus k rather than n minus k over n. And so the minimum value is 1 rather than 1 over n. Okay, so we'll have to redo the calculations, but I'll leave you to do that, and you can also see the lecture notes for detailed calculations. So there might be some typos here. Okay, so do the calculations more carefully for this model. And if you do the calculations, it turns out that the implied bound is a factor of 2 bigger than the true value, which you'll calculate in your homework problems. But I'm going to skip the details of this calculation because there are some typos here. But I hope the general idea is clear of how you calculate the conductance for this matrix capital lambda, for the set of rates lambda VW. Okay, so those are all the examples we worked through. So I hope the concept of conductance is clear and the statement of the theorem giving an upper bound on the mean Rumour spreading time is clear. So now we'll turn to the proof of the theorem. Okay, so we are going to define Tk as the first time that k nodes know the Rumour. And we'll also define S of t to be the set of nodes that knows the Rumour at time t. And we'll denote S at the random time tk by sk. So sk is the set of k nodes that knows the Rumour at time tk, which is the first time at which at least k nodes know the Rumour. Quite a mouthful, let me repeat that. Tk is the first time that k nodes know the Rumour, so the set of nodes that knows the Rumour at time tk has to be of size k, and we'll denote that set by sk. In studying Rumour spreading on the complete graph, we didn't care which set of nodes knew the Rumour at time tk, right? Because by the symmetry in the problem, it didn't matter. Any set of k nodes was just like any other subset of k nodes. But for arbitrary graphs, that's not true. The sets are different, and there is how much longer it takes for one more node to learn the Rumour is going to very much depend on what the set sk is. It could be very different for different possible sets sk. So if we wanted to do an exact analysis of this model, starting from a single vertex knowing the Rumour, we would have to consider all possible sequences by which these sets sk grow to become the set of all vertices. So we'd have to keep track of all possible S1, all possible S2, etc., and then work out these times tk plus 1 minus tk, which depends on sk, the conditional distribution. And since there are 2 to the n subsets, it's not realistic to do that, and that's why we can't do an exact calculation in this case. So we need to keep track of sk, but it's too hard to do that. So we are going to get bounds which depend on sk only through k, and let's see how that happens. But first, conditional on sk, if I tell you what sk is, what's the total rate at which nodes which know the Rumour contact nodes that don't know the Rumour? Sk is the set of nodes that know the Rumour. Sk complement is the set that does not, and lambda VW is the rate at which vertex V contacts vertex W. So you have to add this up over all pairs of vertices where V knows the Rumour and W doesn't, right? So you have to take the sum of this over all V in sk and W in sk complement. And so the random variable tk plus 1 minus tk, conditional on sk, is exponentially distributed with this parameter, the sum of rates. And so its expectation is 1 over the parameter, so it's 1 over the sum of rates. This is the conditional expectation given Sk, and it very much depends on Sk, right? So that's the point. That's what makes the analysis complicated for arbitrary graphs. But now we are going to use a bound on this denominator. So we are going to obtain an upper bound on this conditional expectation by obtaining a lower bound on the denominator. And the lower bound is the following. We know that the conductance is the minimum over all subsets of this quantity divided by this quantity. In other words, for any subset Sk, the ratio is at least as big as the conductance. The conductance is the minimum value over all subsets. So for any subset, it's at least as big as the conductance. And rearranging the ratio, that says that the sum of these rates is at least as big as the conductance times this denominator, which has moved over. And by definition of Tk, the cardinality of Sk is k. The cardinality of Sk complement is n minus k. And so this is what we get. And this doesn't depend on what the set Sk is. And so the conditional expectation of this time is bounded above by the reciprocal of this quantity. And taking partial fraction expansions, this gives us 1 over the conductance times the same expression, 1 over k plus 1 over n minus k as before. Okay, and the rest of the proof is much the same. So we first write Tn as a telescoping sum of Tk plus 1 minus Tk. There's an extra term of T1, but T1 is 0. When we take expectations, we get the expectation of the sum by linearity of expectation. That's the sum of the expectations. Now, this expectation, we don't know. It depends on Sk. So by the Tower rule, it's the expectation of the conditional expectation. Now we use the bound on the conditional expectation. We know this conditional expectation is smaller than this, smaller or equal to this. And so this is a constant. So taking the outer expectation gives you back the same expression. And then it's just straightforward calculation as before. You get 1 over the conductance outside. This sum is approximately log n, and this is the same sum counting down. So we get 2 log n as before. So much of it is the same as for the complete graph. Okay, so that completes the proof of the theorem. And this is the main result we wanted to prove about upper bounding the Rumour spreading time on an arbitrary graph. Okay, so that is the main result for this lecture. So I'll end with a few comments. So how good is the upper bound in general? Is this useful for general graphs? We saw some examples. It's tight on the complete graph, not too bad on the star, a bit worse on the cycle. It turns out it's similarly worse on lattices. It's off by a factor of log n. Log n, you may say log n is not too bad. That's a price you're willing to pay. It could end up being even much worse. I don't know what's the worst it can be, but it can be off by something proportional to n on the dumbbell graph. So the dumbbell graph is 2 complete graphs of size, let's say, a fraction of n vertices on each, and in between you have a long string of vertices. It can be a short string or a long string, and depending on that, you get different Rumour spreading times, and you can show that the bound is poor in this example. As I mentioned in the motivating lecture last time, this is used, Rumour spreading is used as a subroutine in many distributed algorithms, so it has applications in computer science. File sharing algorithms like BitTorrent can be thought of as a variant of rumor spreading. All the examples we looked at, the graph was fixed, but you can also study the problem on graphs which are changing over time, either randomly or under the control of an adversary who tries to prevent you spreading the rumor effectively. So that's an interesting question. Okay, you might be interested, say, in fake news, and in that case, you want to slow down the spread of fake news. So you might ask, can we control these graphs to slow down the spread? Another question that might be of interest is on a general graph. If you start the rumor at some vertex, you don't wait till it reaches everyone, but you wait for some time so it's reached a subset, and you take a snapshot, you know who has heard the rumor, can you find out who started it? So this is important, for instance, in finding out where malware originated in computer networks. For biological epidemics, it might be important in identifying the source of an infection. So questions of this type are important. Okay, so this is all to say a bit more about why we studied this apparently frivolous problem, to say that it's in fact not all that frivolous. Okay, so I'm going to say a bit more. The rest of this talk is mainly for the fourth year students. You have to do a presentation, and I want to give a quick overview of some work related to what we studied in this model, and these are papers you could consider presenting for your end of term presentations. I mentioned already that there are similar results for a much more natural discrete time model, and that was studied first by Fries and Grimmett, and more precise results were obtained by Bittel. You could look at either of these papers for your presentation. We studied a model where we described how the rumor spreads, but it never stops spreading. No nodes never stop repeating the rumor. In practice, that's unrealistic. At some point, they are going to stop. And if you are looking at social networks, then one natural way they might stop is if I'm spreading some rumor to you and you already know it, I think this is no longer interesting news and I stop spreading it. So you could ask what happens if you spread rumors that way. It turns out that when you do that, not all the nodes learn the rumor, only a fraction do, and you can calculate that fraction. And there's this paper by Sudbury looking at that. Okay. I mentioned that the rumor spreading time is not sensitive to the distribution of for the first passage percolation version of the model, it's not sensitive to the density of the edge weights. It only depends on the density at the origin. And that's true if it's finite density at the origin, but what happens if it's infinite density? So you can look at this paper for that. Okay, and then we proved one limit theorem for Tn divided by 2 log n. We showed it converges in probability to 1. We can ask for finer behavior. So Tn is centered at 2 log n. And we can look at the fluctuations and ask, do those fluctuations converge to some limiting distribution? So you can look at this paper for that result. Then we looked at the time it takes for the rumor to spread to everyone, but we didn't look at how many intermediate nodes it passes through to reach a target. If you're interested in that question, look at this paper. Okay, then we looked at, we showed that rumor spreading is equivalent to first passage percolation, and that's asking about shortest path. So what does the length of a shortest path look like? You can look at not just at shortest paths, but at other optimization problems like the minimum spanning tree or the Steiner tree. And you can look at those again in the complete graph with exponential edge weights. So there are some papers studying these problems. Okay, I also mentioned this about what happens if the networks evolve over time. This paper looks at that problem. I mentioned applications that rumor spreading can be used to do distributed function computation. So here's a paper looking at that. Paper looking at file sharing algorithms like BitTorrent, and finally looking at identifying the source of a rumor in a network. Okay, so there's a large amount of related work and papers you can look at to present at the end of the term if you're a fourth year student. Okay, so that ends this topic of rumor spreading. So I'll stop sharing. And next week, we are going to look at a different random process on networks, which is averaging and consensus.